a work published at SecITC in 2018 and realized during my PhD named Binary Data Analysis for Source Code Leakage Assessment. So the presentation will be divided as follows. First, I will introduce the subject, then I will describe the data that we will analyze and two important features, and then propose the applications of this, and finally conclude and propose some further work. So first, I will start a quick introduction of Sidechannel Analysis, even I think that most of you already know, and also the context of the current work. So what do we call Sidechannel Analysis? So first, a side channel, it's a non-conventional channel that is not designed for communication or to be used. Usually it could be power consumptions, electromagnetic emanations, most of the time, and also since few years now, cache is really important side channel. And all this information that leak during the execution of an algorithm could be used to recover secret information. Could be usually due for cryptographic algorithm, but not only. And the A for analysis, it only the fact to apply statistical tools to extract this sensitive information. And historically, the side channel have been used to target cryptographic algorithm, asymmetric, symmetric, hash functions. Most of the time also, historically, it was for embedded device, IoT, smartphone, smart card. But now everything could be targeted by side channel, and not only cryptographic algorithm, also some reverse engineering have been proposed by side channel. So side channel could be used to extract a lot of sensitive information, not only secret key or cryptographic sensitive information. Now let's go to the context of these papers and the study. How can we do side channel analysis without any laboratory? I want to study software implementation, but I don't have any access to the side channel laboratory. No probes, no oscilloscopes. And so in the literature, most of the time, the simulator is the solutions. There is a lot of publication. So Silk, Elmo, Oscar, dynamic binary analyzer are the main known ones. And usually it's do as follow. First, it take as an input the source code or sometimes the compiled code. It uses a simulator. It could be an emulator or an hardware simulator or anything else. And once data have been collected using the simulations, some additional information can be usually used to generate traces. So the software is simulated, then we extract information to generate traces. But in our case, we will stop at the simulation. We will not use any trace generations. And this is inspired by the work proposed at Chess, that is the first side channel attack against the white box implementation that have been proposed in the paper named Differential Computation Analysis. And in our case, we will use GDB to collect this information and then use it to extract some sensitive and weakness on the software implementation. So now let's go through the data and the features presentation. First, I will present how we collect the data and which data we collect. And then I will present two features. First one for realignment and the second one for data reductions. So we will execute our code on a standard machine, an x86 architecture, 64 bits, and we will record as much as information possible. So all the registers, all the 64 registers, all the 16-bit registers, the flags, and also the program counter during the executions of the source code that we are analyzing. For the notations that I will use for introduce the two next features, so we'll store the traces in the matrix X. For one executions, we'll have D for the first dimension. That will be the number of PC change. So each time the PC will change, we will record all the data that we have access, so the registers, the flags, and store this as binary information. So everything will be in binary matrix of dimension D time R. And for each matrix, each data matrix will have a PC value that is 64 integers and that give us the information where the data came from inside the execution. And then if we repeat this for Q time, for Q executions of the software, we'll have each time a matrix of data and a PC vector. Let's illustrate it. Like here, it will be the illustration I will use in the presentation for the data. We have in the left the PC vectors, that is integers, 64-bit integers, and in the right, in the matrix X, we'll have all the bits we need for storage and all the PC that have been executed. And if we take another illustration for a real case, so here it be a trace of the executions of a white box cryptography implementation provided at the CTF of chess in 2016. In the x-axis, it's all the registers, all the 64 registers and the 16-bit registers. Here it's displayed as 64 to 64-bit, just to get like clear illustration. And in the y-axis, it's all the PC values, the index of the PC values. In white, it's the zeros, the bit at 0, and in black, it's the bit at 1. Now, how can we use this data? First, we'll need something important. It's resynchronization. As in usual side channel, when you have traces, power traces, for example, we need to have like resynchronized traces to be able to analyze. Here, it's exactly the same. Because if we have two distinct traces, and inside these traces, two PC have the same values, it means that happens at the same time, at the same line in the code, but not necessarily at the same iteration. So it does not mean that the data belong to the same execution at the same time in the code. So we don't want to align these two data since they are not related. But we need, at the end, we need only one PC vectors for all the Q traces, Q matrices of data we have. So we'll need to resynchronize. And for this, we will focus only on the PC. So here it's what we have as input. It's all our traces, all our Q traces. And for each traces, we have its own PC vector. But we want that all these PC vectors are equal to resynchronize this data. But PC values equal does not mean that it's the same time in the code. So for this, we'll need to introduce two definitions. The first one will be the fixed point. And a fixed point, it's a point that appear a fixed number of time in all the traces. So a PC will appear m times for all the traces will be a fixed point where m is an integer. So it could appear once, two, or multiple times, but for all the traces, the number of times it appears, it's the same. And we also introduce the pseudo fixed point that is a fixed point will be a pseudo fixed point, but not the contrary. And here, a pseudo fixed point, it's a PC that will appear m times or not. It means if this PC appears, we will know how many times it will appear, but it can also not appear in the trace. And we will use these two definitions to resynchronize our trace. For this, we'll use this following algorithm. First, we will get all the distinct PC value we have in our dataset. So all the distinct possible values that could be taken by PC. And we'll call this D prime. So we have D prime number of distinct possible PC values. Then we will compute the accumulation. So how many times for each trace this PC will appear. So here it's the sharp PC D prime Q. So we have D prime that for each PC and Q for each traces. So in each cell of this matrix, we'll have for a Q how many times the PC have appeared. And now, using this matrix, it's easy to find the pseudo fixed points and the fixed point. And we will list this in a FD prime prime matrix, where we extract only the fixed and pseudo fixed points. And a fixed pseudo fixed point will be a line of this matrix that take only two distinct values, 0 and one value m that never change. And once we have this, we can reconstruct a PC vector based on the fixed and pseudo fixed time. We will repeat the PC how many times is MD value. So the number of times the fixed point or pseudo fixed point will appear. And if we go back to the representation, now we can reorder our traces to respect the PC we just created, the PC vector we just created. So at the end, all the data are now aligned, and we only need one PC vector. Then the second features is, do we need all the data that we record for the analysis step? And for this, we will define two metrics. The first one is the activity matrix, and it will be only the sum of all our metrics. And doing this, we will compute the sum of all our metrics over Q. So at the end, it's a D times R matrix. And we will compute the modulus by Q of this matrix. So at the end, we'll have only 0 or once. Once if this value is not equal to Q or 0. So what we do, it's computing the sum, doing a modulus by Q, and if it's a non-zero value, we'll put a 1. And if it's a 0, it means that it's only 0 for all the execution, only 1 for all the executions. So it means that this bit never changed for all the executions. And we need some variance to be able to analyze the data. So here, if there is no variance, it means that the bit does not leak any information. And the illustration, so we have all our metrics of data. We will compute the sum over Q. And then we'll call a new matrix that we define as the transition matrix. And what we will do, we'll compute an end of all the trace executions, but not the trace execution itself, the trace XORed with a shift of this on trace. So what we want here is to check if from a PC to another, the value changed. And it's what we do here. Since we have, so at the time D-1, if you compute the XOR with the PC D, if we have a 0, it will mean that the bit does not change. And if it's distinct, if it's 1, it will mean that this bit has changed between the PCD minus 1 and the PCD. And the goal of this matrix is to find where the bit has changed in order to not reanalyze the same distributions multiple times. And here the illustrations. So we have the trace D, the trace shift here, and we'll compute XOR between both. And for all this XOR, we'll compute an N between both. So at the end, we will add identified using this T matrix, the transition matrix. We have identified, we have removed the distribution that does not change over D. And for the first matrix, we remove the bits that does not change over Q. And now we'll define the point of interest, the point that can leak information, by the list L. And this sample, so a sample will be a PC value and an R index, so which register for which PC that change. So we want that it change over Q and it change over D. So we want that both metrics add a 1 to be in the point of interest. So now we can flat our traces. So for each traces, we just extract the L samples. So now I will say samples, but the samples, it's a pair, one PC value, and so the index where is executed in the code, and which bit of which registers. But here it's now flattened. And if we apply these reductions, we still are using the same white box implementation. The first here we have the activity matrix. So we can see that over Q, some bits have been removed. If you remember the first picture, we had really black here, and now it's removed. It means that this register never changed over Q. And when you remove the sample using the activity matrix, you conserve only 4.63% of the initial samples. Then, if you use the transition matrix, so you only conserve the samples that change over D, you conserve only 0.4% of the initial number of samples. And when you combine both, you only conserve 0.29. It means without this, you will analyze, without removing, like denoising the trace, you will analyze more than 99% of the data you will analyze will be useless. And now let's go to a practical result and application of this work. So let's first quickly introduce the AES. So the AES take an input a plain text, and 100, and here we will analyze then 128 AES. First, we'll do XOR with the key. We have a subbyte, so the nonlinear functions, and then two linear functions, shift row and mix colon, and this is repeated 10 times to get a ciphertext of 128 bits. And then what we call the white box implementation, because the first pictures and the application of the features have been applied on a white box implementation. But what is a white box implementation? White box implementation, it's a cryptographic algorithm where, when it's implemented, the secret key is hidden inside the code. So, for example, it could be an AES. Here, in our case, it will be an AES. where inside the implementation, so inside the source code, inside the C code you have, the key is hidden inside the implementation. But for this, it's huge successions of lookup tables that have been computed during the creation of the source code. So it's really like, it could be billion of lines of codes just to create like lookup table where the key is hidden inside. And now I will define a leakage model, because usually in Sidechannel you have the traces and you try to submit some leakage, potential leakage, and compare with the traces in order to see if the data can reveal leakages. And in a previous paper, author proposed some optimization to the usual output of the S-box for the leakage model. But they did as leakage model the output of the S-box, and the computation, the 2 times the output of the S-box and 3 times the output of the S-box. They analyze also these 2 computation as leakage model. But if you combine all of this, you will not have like 3 times 8 bits, but only 18 bits. Because you have some redundancy computing the 2 times and 3 times the S-box. So then you have the size of the model, it will be S. The number of traces we need to recover the secret, it will be Q. For each byte we target, we have 256 possibilities, and we will repeat it for all the bytes. So since it's a 128 AES, we will use 16 bytes. We'll repeat it 16 times. And so here it's what we have for our analysis. So we have the traces, the flattened traces. So it's binary data. So it's just a succession of bits that have been extracted from registers and PCs. And here we have all our leakage models that also are binary. Here it's a binary matrix. So for example, if we take the first one, it will be the output of the S-box, 2 times the output of the S-box and 3 times the output of the S-box for the byte 0, if we guess that the key is equal to 0. And we will do it for all the possible key values, all the bytes, all the traces, and all the distinct S model. And now what we will use, we will compare all the distributions here on the left to the trace on the right. And for this, we'll use the Pearson coefficient correlation, that is the covariance divided by the product of the standard deviation. But since we use binary data, we can simplify this matrix using the accumulated formula for the Pearson coefficients and remove this, since when you do the product, the sum of a product in a binary, it will be only the sum. And now here we have the results. So what do we have here? It's all the 16 bytes of the AES. And in gray, it's when we submit a bad guess. And in color, it's all the 18 bits of our model that can leak information. So here we can see that we have peaks for all of this. It's not always the same bit that seems to leak, but we can identify leakage for all of them. And so using this, we can recover the secret key only using the C code. But more than this, we can link our result to the source code. Once we have identified the bit that leaks in our traces, we can go back to the source code and find which a register, oh, sorry, which register is leaking, which bit of the register is leaking, which sensitive value is leaking. So here it's the output of the S box, but which bit of the output of the S box is leaking? It's the bit 7. And for example, the next line will be that in the register RBP, the bit 0 of this register will leak the bit 4 of 3 times the output of the S box. So now let's conclude the presentation. So in this paper, we propose an end-to-end solutions to analyze source code without any side channel material, so any laboratories. We propose 2 features, one for denoising and one for realignment, and also take advantage of the binary aspect of the data. And as a further work, it could be really interesting to apply this methodology to other data providers. I did it also at the end of my PhD on hardware simulated traces, so using model sim and applying almost the same process. And also it's planned to do the same and to use some of this idea on traces extract from QEMU simulator by an internship in few weeks now. And I think also that it could be really interesting to improve the analysis, because as you see, there is a huge amount of data. We found a nice way to reduce this amount of data. But if we want to mount second order data, second order attack or things like this, it's needed to improve even more the analysis. And maybe as a next step, what could be extract using machine learning or deep learning algorithms, since it's kind of trendy in Sidechannel now, on this data set. What kind of informations could be extracted? Can we extract more information using machine learning or deep learning in this case? Thank you for your attention. Do you have any questions?